terms of time slots. So it's this talk is up to 3:25. From 3:25 to 3:50 is the next talk by Rajesh on Hadoop and cloud storage, and from 3:50 to 4:15 is Anindya Shankar talking about machine learning, and then we have the break. Thank you. Uh, just a quick one for people standing there. If you don't mind sitting in this area over here, it's easier if that's okay. Otherwise, it's fine.
Hello, good afternoon. Thank you everyone for coming. My name is Akshay. I am an engineer at LinkedIn. I work for the Hadoop development team. In this presentation, I'll be talking about how to optimize your Hadoop cluster by tuning the jobs that you run on them. So I've divided this session into kind of three phases. So to begin with, I'll talk about performance in Hadoop, some of the challenges users face while tuning job. And then in the second phase, I'll share some of our learnings, some of the things we did to address these challenges. And then in the third phase, I'll talk about a tool called Dr. Elephant. It's a self-serve tool to help users easily optimize and tune their Hadoop and Spark jobs. So before we begin, I'd just like to talk a little bit about Hadoop at LinkedIn. This will help you get a better context of what I'll be speaking in this session. And also scaling in Hadoop, how does that work? So in the year 2008, when we started with Hadoop, we started out with a single cluster with about 20 nodes. There were hardly about 10 users and about 10 workflows running in production. They were predominantly written in Java, MapReduce, and Pig. So fast forwarding to 2016, we now have more than 10 clusters. There are more than 10,000 nodes, more than 1,000 users, thousands of workflows running in development, hundreds in production. And now people use a variety of frameworks, including MapReduce, Pig, Hive, Spark, Scalding, and others. So how do you scale Hadoop? Simple, you add extra machines to the cluster to improve its performance, right? So you already saw how we from a single cluster with 20 nodes to 10 plus clusters with 10,000 plus nodes. But there's one issue here. Hadoop, though Hadoop is scalable, that is, you can add extra machines to improve the performance, Hadoop does not guarantee an optimal working cluster solution for you, right? So even if you add extra machines, the given cluster may not have the right configurations. Even if you run a job, Hadoop doesn't guarantee that the job will run optimally on the cluster. In addition, you cannot keep throwing machines to improve your performance forever. Adding machines is a huge investment. So once we decide that we need to tune the given resources, once we know that we cannot keep adding extra machines, we need to try and get the same performance by tuning the given resources, right? And once you decide on tuning, you need to start measuring the performance of the cluster. So measuring performance will highlight some of the hardware failures in the cluster, some of the poor performing components in the cluster. It also gives you scope to upgrade your cluster. Maybe you want to upgrade the version of Hadoop that you're using. You might want to update the disk, update the CPUs, right? So once we start measuring performance, then we can think about tuning specific things on the cluster, right? So I've divided Hadoop tuning into two broad categories. So one is the cluster level performance tuning, and the other is the job level performance tuning. So by cluster level performance tuning, I mean tuning your network bandwidth, your input output to disk, your CPU cores, and other cluster metrics. Now we already have a lot of cluster monitoring tools like Ganglia, which help you tune your clusters. You can even take help from an Hadoop expert to do all of these. But what I'm more interested in is, or rather another important part of tuning your Hadoop cluster is tuning the jobs that you run on them, right? Why is it important to tune jobs? Because we usually schedule our jobs to run periodically. We run it daily, we run it hourly, and they keep running infinitely until they actually break, right? So if your job is not tuned, then over a period of time, it's going to consume and waste a lot of resources. So how do you come up with a cluster where all your jobs are running optimally? So here's what we tried at LinkedIn. What we did is we created a production cluster, and we made sure that we let workflows go into this production cluster only after verifying it is tuned. So the Hadoop dev team would act as kind of a production gatekeeper, and we would make sure that users can run their workflows in production only after verifying it is tuned. But there's one problem. This is this kind of restriction to the users. Users are running their workflow successfully now, but we want them to tune the cluster, and then only we say you can run it in production. So we started receiving hundreds of emails from users asking us how to tune a Hadoop job, and we started helping them out. But how difficult is it for the user to tune a job, and to what extent one can help them? Hadoop itself is designed to let users tune their jobs, right? But there are a couple of challenges with it. One cannot optimize Hadoop jobs they write without them understanding the internals of the framework, right? And even if you decide on tuning your job, the information required to tune your job is scattered. So in most cases, people usually use some high-level tools like Pig or Hive to run their Hadoop jobs, and where they are just exposed to a console or a terminal where they can just see some client logs. If you want to tune a job, it's not just enough if you look into these client logs, but you also need to go look into your resource manager logs, your application master logs. There are job configurations, there are job counters, there are task counters, and each task will have a different set of counters. So there's a huge library of information, and this is just for one MapReduce job. If you run a Pig job or if you run a Hive job, that might trigger say 100 other MapReduce jobs, and then you can imagine how complex tuning becomes, right? And thirdly, Hadoop has a huge set of parameters, and it's really unfair for you to expect someone new to know the significance of each of these parameters. These parameters are also interdependent. So if you tune one parameter, it might affect some other parameters also. So in short, I would say you cannot tune what you do not know, and you cannot improve what you cannot measure, right? So how do we do this? How can we help the users? All these challenges put an extra burden on the users. It tries to lower their productivity. So how can we help the users? How can we improve their productivity? So we started out training users. We would keep regular training sessions and teach users how to tune a job. We would say what parameters you can change, what parameters, what is the effect of changing a parameter, what is split size, how can you change split size, what's min split size, what's max split size. We start teaching them all of these, and gradually they pick up how to tune jobs, and then they do it on their own, right? But there's one problem here. This doesn't scale. So as more people started joining LinkedIn, as more people started onboarding onto Hadoop, we had to keep up with these trainings, and people coming were from different Hadoop backgrounds. Some did not know anything about Hadoop, some were experts in Hadoop, and people use different frameworks now to run Hadoop. Some use Pig, some use Hive. So our trainings had to be specific to our audience as well as specific to the framework that they started to use. So at some point we started realizing that we were spending way too much time training users and focusing away from other important issues. So how do we solve this? So what we next tried to do is, rather than educating users, rather than training users and asking them to tune, why not have some experts review it on behalf of the users? So we had the Hadoop dev team, some experts in Hadoop dev team review workflows on behalf of users and give them specific suggestions on what you can change to improve your workflow. So this again sadly has a problem with scaling. So again, if you have more people in Hadoop, there are more workflows in development, and the probability of more workflows going to production, right? So there are more review requests keep that coming. But the number of experts are limited, right? But there are a couple of other issues here also. Typically how this works is a user would set up an appointment with the Hadoop team. He would then go talk to a person from the team, get suggestions. Then he would go back, make changes to the workflow, and he would set up another appointment to with a Hadoop dev team to review it again. Now, by the time he does that, the Hadoop expert would have reviewed 100 other workflows, and it's difficult for him himself to keep track of what suggestions he gave earlier, right? And what happens here is sometimes this happens the to and fro, a lot of to and fro. So user reviews, he goes back, the expert says some other changes, and he goes back. So sometimes it takes months for a workflow to go into production. And the other issue here is we really do not know by changing specific parameter has it really improved the performance of the workflow. Right? You cannot actually compare your current execution after you make the change with an execution before the change. And these reviews are subject to human errors. Some expert might overlook certain aspects. Different experts might have a different opinion on the matter. Right? It's sometimes difficult to come to consensus. So both training and expert reviews did not work as we started growing. At this point in time, we did not have a clear picture on how to solve this issue. We couldn't even go back, and the help requests kept coming, and we had to spend more of our resources helping them out. So here's a lesson that we learned from here, that is, scaling Hadoop infrastructure is hard, but scaling user productivity is much harder, right? So this is when we decided that we will try out an exploratory intern project to fix this problem. So we will build a tool to automate all of this. But what's the idea? How will we do this? While doing these expert reviews, we came across several common repetitive optimization patterns. And we thought we will gather all of these patterns and feed it to this tool as a rule. And this rule will automatically now analyze all the jobs that are running on the cluster for the existence of this pattern. Right? This is what gave birth to the tool called DocTelFin. So what is DocTelFin? It's a self-serve performance monitoring and tuning tool for the jobs that you run on the cluster. What does it do? It helps every user get the best performance out of the job. Right? It's a self-service tool for the users of Hadoop. People who run Pig jobs, people who run Hive jobs, people who run Spark jobs, they can go to DocTelFin, search for their job, and get insights into how their job performed on the cluster. And DocTelFin will then make suggestions like how you can improve your workflow, what parameters you can change to improve the efficiency of the job, how can you speed up your job, all those things. And you can even compare and analyze your historical executions. It's also a platform for other performance-related tools to make use of this and come up with some new metrics. Here's a high-level architecture of the tool. At the top, you can see a job generator. So what this does is it fetches the application from the resource manager periodically, say every minute. And once it gets a list of application, then depending on the type of the application, whether it is MapReduce or Spark, there's a separate fetches. There's a MapReduce fetcher and there's a Spark fetcher. The MapReduce fetcher will start fetching all the information that it can get for that application. Say it will query the job history server, get all the information for that job. And then similarly, there's a Spark fetcher which will fetch all the Spark related information from the Spark history logs. Now, once you have all the information for a given application, we have now fed these rules into DocTelFin. There are MapReduce specific rules and there are Spark specific rules. They will run over these data and then they will classify the job as critical or safe. And then you save it in the database, and then there's a UI where you can go and look into how your job performed on the cluster. So I'd like to discuss a couple of rules that it has. So one is the mapper data skew. So what is this rule? When you run a MapReduce job, it runs a set of mappers and set of reducers, right? If there is a skewness in the input to the mappers, then we say there's a skewness in the input on the mapper side of the input. So for example, here you can see there are blue boxes and then there are yellow boxes. The yellow boxes are input to the mappers, and the blue boxes, which are the mappers, the height of the mapper represents the runtime of the mapper. Now, suppose mappers 1 to k are reading a larger split of data, mappers k plus 1 to map n are reading a smaller split of data. Now, mappers k plus 1 to map n, which are reading a smaller split, will relatively complete sooner than the other mappers. And once they complete, they have to wait for all the other mappers to complete. So ideally, we want every mapper to get the same amount of data, so none of the mappers have to wait for other mappers to complete. So how do you fix this? What you can do is you can combine all these smaller splits of data and feed it to a single mapper. If you go to Dr. Elephant, it will tell you what specific parameter you can use. I think it's the combined file input size. If you set that, then all the splits will go to a single mapper. But what's the cause of this? Why does this happen in the cluster? One reason is, suppose you have your file which is a little larger than your HDFS block size, right? In that case, your file gets split into a block size and then a smaller chunk. Now, if you have a large number of files, then there will be a large number of smaller chunks that will be formed. And the framework, what does the framework do? It allocates as many mappers as there are these number of splits. So how can you fix this? You can set a combined file input size, and all these smaller chunks will get combined and go to a single mapper. Another rule, mapper memory. So when you run a MapReduce job, you request certain container size from the resource manager, and then your job runs within that resource manager. Now suppose that the user requests say 4 GB of container, but the job, when it runs within that container, just uses say 500 MB of it, right? So the problem here is you are actually requesting more resources, which means you're relatively going to wait for more time for this 4 GB of container to get allocated. And even once it gets allocated, you're not going to utilize the entire 4 GB of resources. You just need 500 MB of it. And you're actually blocking 4 GB of resource on your cluster. So what you can do here is you can request a lower memory by setting mapreduce.map.memory.mb. That's for the mapper container. If for a reducer container, you would set mapreduce.reduce.mb. So all these suggestions will be given by Dr. Elephant to the users. Now, these are two of them. There are a bunch of other MapReduce specific rules. There are a bunch of Spark specific rules. The Spark specific rules are not as vast as the MapReduce. They are still in the early stages. If you go to Dr. Elephant and search for your job, you will see a result. So the highlighted rectangle is one specific MapReduce job. And then you can see a username, that's the user who ran that job. And pig represents the pig job that triggered that MapReduce job. And then there's a job ID. And below that, you will see these colored rectangles. Now, these are the rules. So you can see at the leftmost, there's a mapper data skew, then there's mapper time, mapper speed, mapper spell, all the others. The color of the box represents how severe it is. So if you click on that specific job, you will get a report on that job. So here's a small snapshot of some of the heuristics. So here at the top, you can see mapper data skew. It's saying the job is severe. And why? Because there's a group A which has 197 tasks. Each of these 197 tasks are reading an average of 9 MB. Then there's a group B which has just 3 tasks, and each of these 3 tasks are reading 512 MB. So you can see the skewness here. All those 197 tasks which are reading 9 MB will complete soon, and then they have to wait for the other 3 map tasks which are reading a larger chunk of data. And if you click, there's an explain link. If you click on an explain link, and then it will tell you how you can fix that problem. So similarly, below there's a mapper memory which I explained. It is also severe here. You can see the average physical memory, that's the memory it took in the container, that is 658 MB. And at the bottom of that same box, you can see a requested container which is 4 GB. So he has actually requested 4 GB, but using just 658 MB. So it would be ideal to request a lower value for your requested container memory. You can look at your history. You can look at your jobs history. You can look at your flows history. So at the top, you can see a performance graph of how your job or your workflow performed. At the bottom, there's this table which shows all the executions. At the topmost, you can see the latest and then the previous and so on. Each of these colored bubbles represent a rule. The color represents the severity of it. Now, say, for example, your workflow is running on your cluster, you scheduled it, and today suddenly your workflow failed or your workflow took a longer time to finish. Then you can actually come to Dr. Elephant, look at your execution, and probably what will happen is your color in one execution might be green, and in the next current execution that took longer might be red. So you can identify which specific rule is that, which specific dot is red, and then you can just hover over that dot, and it will give you information like what was the requested memory, what was the delay, what was the runtime. You can then actually debug, was it actually your job that took that long, or was it because it was waiting for resources to get allocated? So you can do all such kind of analysis. Maybe suppose you want to change a specific line in the code, you want to change a specific parameter in the code. You can then, by changing that parameter and running, you can then actually see how it has reflected in the performance of your job. Has the performance improved? Has the wait time improved? Or has the wait time reduced? Or has the runtime increased? You can do all such kind of analysis by looking at your jobs history. So how do you define a rule? A rule has an input, a logic, and an output. The input are the task counters, the task data, all the inputs for MapReduce. And then you do some logic over these task counters, you compute a value, and then say if this is greater than a threshold, then you classify that job as critical. If it's less than this threshold, then you say it's green. In Dr. Elephant, we have 5 different output levels. Red indicates it's critical, and then there's orange, which is severe, then there is yellow, which is moderate, and then there are low and none, which are represented by green. So ideally, you want everything to look green for your job. What can you customize in Dr. Elephant? You can write your own rules. So if you have an idea, if you have experience tuning MapReduce jobs, if you have experience tuning Spark jobs, and if you know how to tune a specific job, then you just convert it to a rule. You can look at the way how other rules are written, and just by looking at them, it's very easy to write a rule. Once you write a rule, you test it out, and then you write a help page explaining what that rule is, right? And then you also say what parameters you can set to fix that rule. And once you have the rules and once you have the help page, you can just go to Dr. Elephant, and there's a heuristic conf. Heuristic is a terminology in Dr. Elephant for a rule. So you can go to this heuristic conf.xml file, and you can add 2 new heuristic tags, and then give a path to your class and give a path to your help page and give a name for your rule. And you just restart Dr. Elephant, and Dr. Elephant will start analyzing all the jobs with the new rule that you have written. What else can you customize? You can change rules, you can disable rules, you can change their threshold levels, you can expand to other schedulers, you can expand to other fetchers, you can expand to other application types, other job types. Almost basically everything is pluggable in Dr. Elephant. So earlier I talked about something called production gatekeeper. So I said that we maintained a separate cluster for production, and the Hadoop dev team would act as a production gatekeeper to make sure that workflows go into production only after it is verified, it is tuned. So now now that we have Dr. Elephant, the Hadoop dev team just can refer the Dr. Elephant's report and then see if everything is green, then you can directly go and run your workflow in production. But if there is something, then you can just ask the user, go back and fix this and come again. But this is again a manual process, so what we did is we created a tool to do this. So we created a Jira bot, so a bot that is integrated into Jira, and the user just has to create a Jira ticket and give an execution to its flow, right? And this bot will automatically fetch that execution, get all the reports from Dr. Elephant, and if everything looks green, then it goes ahead, comments back to the user saying everything is good. If there are some issues, it comments back, asks the user to go back and fix them. And if everything looks good for the tool and it goes to production, creates a project on production cluster. If there is some setup to be done, give permissions to the user, it does all of that, and the user can go and run his workflow in production. So this entire process is now replaced, like the tool itself does it. So about 80% of the workflows go into production using this tool without the intervention from the Hadoop devs. What else can you do? You can monitor, you can use these reports to do other kind of performance analysis and reporting. For example, we have a tool that generates daily reports saying what were the top 25 workflows to tune today, what were the workflows that were failing continuously in the cluster today. And there are other tools which make use of these reports to do cost to serve analysis, to compare different revisions of your workflow and others. Good news, we open sourced this year in the month of April. Since we open sourced, we received an overwhelming response. There were more than 60 pull requests. Since we open source, there are more than 10 contributors, more than 50 topics under discussion. I welcome you all to contribute and make suggestions and feedback. One thing that would be good is we can all collectively gather all the good practices, all the good optimization techniques that we have, and feed it into Dr. Elephant and make it as a single hub where to analyze any job completely in Hadoop. Any job that you run in Hadoop, you can do it with Dr. Elephant. Since we open sourced, a lot of companies have shown interest and they have started using Dr. Elephant. A couple of them have running it in production. There were folks from Airbnb who added support to Airflow scheduler. There's a pull request on Oozie. There are a couple of pull requests trying to scale the fetches, and a bunch of other pull requests adding new features and bug fixes and all of the others. A roadmap of Dr. Elephant. So we are soon going to add real-time support for the Hadoop jobs, show analytics for failed jobs, visualize your workflows and jobs through dependency graphs, and also as we expand to other rules, we expand to other schedulers and other frameworks. Couple of references, you can go check out LinkedIn's engineering blog. There's an article on Dr. Liffent. If you want the source code, it's on GitHub. There's also a mailing list and a Gitter chat, so feel free to discuss and share your ideas. And it was also presented in the Hadoop Summit last year. Thank you.
Can we monitor Spark SQL here? I'm here. Here.
Okay.
Okay. Spark SQL runs on Yarn. Can we monitor via Dr. Elephant tool?
Yeah, so as long as you run your framework on Yarn,
Okay.
it can analyze any job that you run there.
Okay. And by default, it uses MySQL, right? In case if I need to change it to Postgres as a meta store.
Yes,
So
you
what
can
is a
it's a play configuration, so you can change your backend as you wish.
which specific configuration file? Because when I tried changing from MySQL to Postgres, I was not successful actually.
Okay.
So
Okay.
there is one appconf folder. There is one elephant.conf, right? So that is a place where we need to change the Postgres.
Okay. Maybe you can bring this up in the mailing list, and we can discuss it from there.
Hey, hello. Yeah, so it will not work with the Spark with Cassandra or something other than Hadoop.
It right now we have support for MapReduce and Spark.
Spark may be running on Mesos or.
Right. We for Mesos we don't have support right now, but you're welcome to contribute and add that suggestion.
Okay,
There's already someone who raised that in the forum, so to add support to Mesos. So that's something we would look forward to.
Okay. Thank you.
Here. So, like you said, right, that one pick job can launch multiple MapReduce jobs. So, is there a place where you can see RAM, CPU, or average, max, min of mapper and reducer all in one place for all the MapReduce jobs that the pick job launched, that pick script launched?
So that's what I mentioned in the end, that we will visualize these things through a graph. So then you can actually click on your pick job and see what were the other pick jobs, the other MapReduce jobs that were triggered by that.
Okay.
You can actually look at your entire workflow and drill down to these.
And you can see the RAM, CPU taken by each job.
You can look into all the Hadoop specific parameters. By RAM, I don't understand. That may be a cluster metric. This is more of a metric for the users to tune their jobs.
Okay, you can't see that RAM because counters are not user friendly. Okay, that's fine. Okay, thank you.
You mean these profiling information for a job? Yeah, that is something that we are looking forward to do that in Dr. Liffent.
I'm afraid we're out of time for more questions, so if you could take the questions offline, that'd be great.
Yeah, I'll be here throughout the day, so you can catch me up and ask questions if you have.
Okay, while the next speaker sets up, just a quick announcement, car with registration number KA03D1103, KA03D1103 is blocking another car. If it's yours, could you please talk to registration desk? Someone asked about returns for food tokens. Indeed, you can exchange them for discounts on t-shirts. So don't throw them away. Do feel motivated to go back to the registration desk. What's the question, sorry? That's what I would assume. Yes, you could find out more at the registration desk. Unless there's this depreciation or interest.
Is this on? Hello. Hello.
So,
Does it work?
just a quick one about the schedule. So we're going to start with
Hello.
Rajesh's session
Oh,
immediately,
no, it doesn't seem to work.
and then this session goes on until 3:50. So there is no
No,
break after that. Immediately we start off with Anindya's talk on machine learning
Okay.
at 3:50, and that goes on until 4:15,
Hello.
when we have a half an hour evening break.
Hello.
And then the next session starts. So if you're looking for a
Sure,
break,
sure.
your next break is at 4:15. So maybe once people settle in, if you need to go out for a toilet break, feel free to do that in small numbers. People have been asking about breaks. Okay, thank you.
Oh, no, that's fine. That's fine. You can just. Good to go? Okay, thanks. Good afternoon, everyone. Welcome to Hadoop and Cloud Storage, Object Store Integration in Production. I'm Rajesh Balamohan. I'm a TASE committer as well as a PMC member. I've been mainly working on the performance aspects of TASE and I've been using Hadoop for quite some time. I'd like to acknowledge two of my colleagues who have done a lot of work on this area, Chris Norath as well as Steve Laughlin. Both of them are Hadoop committers and PMC members. They are mainly working on the HDFS area and very long time users of Hadoop. So here is the high level agenda for today's talk. In the first half, I'd like to talk about the Hadoop cloud storage integration use cases, the Hadoop compatible file system architecture and so on, and some of the recent enhancements that we have made in S3A file system connector. And the second half, I'd like to talk more about the Hive access patterns and the performance benchmarks that we have carried out with Hive test bench, which is nothing but a subset of TP-CDS queries for doing the benchmark on cloud. So first question is like, why do we even need Hadoop in the cloud, right? So if you look at it, Hadoop does not have any, or like cloud does not have any upfront hardware cost associated with that. So what it means is that within a matter of minutes, you would be able to bring up a lot of nodes and then set up your Hadoop cluster with no delay or so. So and also especially you do not need to have an administrator who is going to look after the Hadoop cluster for 24/7. So there is no monitoring cost involved as well. And cloud supports elasticity. So what I mean by that is you will be able to add or delete nodes in a lot more easier fashion in the case of cloud. And cloud also brings up a lot of interesting deployment models. Just to give an example, let's say you have a use case wherein you would want to use the cluster or bring up and use the cluster only for a couple of days or for a couple of hours. You would be able to do that easily in the case of a cloud environment and bring down the cluster pretty quickly. So you are going to pay only for the amount of time that you are going to use the cluster for. So you'll be able to use the ephemeral or bring up the ephemeral cluster and bring it down pretty quickly. Or based on use case, you'll be able to run a very long running cluster as well. And that brings an interesting point. The reason is business units now will be able to go in their own speed as well as budget. So this slide talks more about the evolution of various different integration patterns with cloud storage on Hadoop. So there are a couple of diagrams over here. The first one is an integration pattern where the entire data set is available in HDFS and the applications read the data from HDFS directly, process them, and then store it back onto HDFS directly. At some point in time, the management or the administrator might choose to say that, hey, I have too much of data, I don't need the cold storage to be available over here, so cloud storage is going to provide me a lot more cheaper option, so in which case they might choose to transfer some of the data from the HDFS onto the cloud storage. So they can do that, or they can transfer the data from HDFS onto cloud storage in a lot more easier fashion with tools like Hadoop DisCP. So you can have, with DisCP, I guess most of us know that, where you can have the source URL pointing to HDFS and the target URL pointing to cloud storage in terms of transferring the data. And if you have to restore the data back, you can use the similar tools in terms of transferring the data. Right? The second integration pattern is moving more towards or a step closer to the cloud storage itself, wherein the application directly reads the data from the cloud storage itself, processes them, but the storage is going to go through two-hop approach, wherein the first hop is going to be writing onto HDFS, and later point in time using a DistCP tool, it will be transferred from HDFS back to the cloud storage. The reason for doing this is that there are certain cloud vendors, it's quite possible that the cloud vendors do not have the similar kind of semantics that HDFS expects. Just to give an example, Amazon provides eventual consistency, right? But HDFS expects a lot more strong consistency. So you'd want to eliminate those factors. If that is the case, you'll have to go through writing the data onto HDFS and then move towards or copy the data onto the cloud storage. The last diagram talks more about the end goal that we would like to go or head towards, wherein the data is directly read from the cloud storage by the applications, process them, and directly write the data back onto the cloud storage itself, right? But still, we would like to retain HDFS as a storage medium for storing the intermediate data. So just to give an example, let's say you have a very large pipeline of ETL job or so, which spans across some 10 intermediate stages or so. You don't want to store the intermediate data again and again onto the cloud storage environment, because the performance characteristics in terms of transferring the data might be a little different. So in those situations, you might want to store the data onto HDFS itself and store the final data onto the cloud storage. So what are the kind of problems that we have in terms of moving towards the goal that I mentioned in the earlier slide? Right? So if you look at it, cloud object stores are mainly designed for scale, cost, geographic distribution, availability, and so on. However, there are certain challenges associated with that. For instance, how do we even make sure that the Hadoop apps that are being developed are going to seamlessly work in both HDFS as well as the different cloud object stores? So just to give an examples of problems, take an example of consistency. HDFS offers a lot more strong consistency model. However, in the case of certain cloud vendors like Amazon, it provides eventual consistency. And if you look at the older model, HDFS and MapReduce were sitting on the same node, and the compute was pretty much pushed onto the data where it was located. But in the case of cloud, it's totally different, right? Where the storage is completely separated out and the compute is available in EC2 or like different cloud vendors. So the performance characteristics might vary a lot. And cloud storage are basically not designed for file system like APIs or like usages. And there are certain limitations with the APIs themselves. Just to give an example, in the case of HDFS, a rename is an atomic operation. But in cloud vendors, it may not be. Again, taking an example of Amazon, the rename is a copy and delete operation, so it may not be atomic over there. So there are certain semantic differences between HDFS and what the cloud vendors might end up offering. So what is the goal, right? I mean, if you look at it, the primary goal is to be able to integrate with the unique functionalities that are provided by different cloud vendors onto Hadoop itself, and to be able to optimize each of these storage connectors that we have with different cloud vendors. And also not only at the connector level, but also we would like to optimize at a higher levels, like you could have optimizations in Hive, Pig, or Spark, or like MapReduce, or in cascading, and all those places, right? So we would like to optimize at a higher level as well, so that they will be able to make better use of the connectors. We'll talk about the performance optimizations at later sections. So this slide talks more about the Hadoop compatible file system architecture. So if you look at the different applications, right, I mean, be it MapReduce or like Hive or Spark and so on, they do not directly talk to the file system level implementations. So they go via an abstraction layer, which are a set of interfaces as well as abstract classes like file system, file context, abstract file system, and so on. And beneath that, you have the strong or the implementation details like HDFS and so on, or the concrete classes basically. I'll cover the HBase part a little later. But if you look at the underneath layer, we had HDFS, but now we have a set of different providers like WASB, which is from Microsoft, which is a blob object store from Microsoft, ADL, which is Azure Data Lake, again from Microsoft for big data analytical workload. You have S3 from Amazon, and GCS from Google Cloud Storage. These are some of the cloud storage connectors that are already available in the market. So as mentioned earlier, WASB is from Microsoft, and it's a blob storage connector or blob storage platform where it provides a really strong consistent model, and it also offers very good performance that you can even run HBase on top of it, and strongly consistent as well. The reason why I mentioned I'll cover HBase earlier, I mean later point in time, was that HBase has got some strict semantics that needs to be adhered with HDFS. So WASB offers that. So it's really strongly consistent as well as offers a good performance. Similarly, ADL is from Microsoft Azure Data Lake, offers strong consistency as well as it's tuned for big data analytical workload. S3A is from Amazon, offers eventual consistency model. Hortonworks has an external Jira open for making it an optional consistent model, and a lot of performance improvements are in place, and it's very actively developed in the Apache world. EMRFS again is from, it's a proprietary connector from Amazon for their EMR cluster, and it offers an optional consistency model or strong consistency model at an additional cost. Google offers GCS, it provides multiple configurable consistency policies, offers good performance as well as they are planning to open source it pretty soon in Apache. I'd like to take a case study with S3A and talk about more about its functionality as well as the performance characteristics. So as mentioned earlier, one of the main objective was to be able to integrate with the unique functionalities that are provided by different cloud vendors and then bring it onto cloud itself. Classic example is in S3 is that it offers multiple authentication models, almost like 5 or 6 of them. So it offers basic authentication model wherein you provide the access key as well as the secret key onto Hadoop configuration file itself, and at runtime Hadoop will be able to pick up those details and then connect to the S3 buckets. Disadvantage of this particular approach is that the moment the configuration files are exposed to anyone, they will be able to retrieve the keys, and there is a possibility of accessing the buckets later point in time. Or you could have the EC2 metadata itself where Amazon or AWS directly writes the credential information onto the EC2 instances itself, and using APIs, you will be able to directly read those credentials and then process your data in the S3. It's a lot more secure option. The reason is you're not exposing any of the credentials anywhere in the configuration files or so. It also supports an option of environment variables where you can set the environment variables and then to provide the credential details. A lot more less secure option, but might be useful for some applications. And it also offers session credentials where you could temporarily create a credential from the token service of Amazon, and which will be valid only for some amount of time. So that's a lot more secure option if you have to reduce the amount of credential leaks that are going to happen. Or else if you have public data available, you could even have anonymous login. So different type of authentication models are there in S3, which is supported now. Also, it offers encryption, that is in the server side. You could transparently encrypt the data which is going to be stored on the S3 with AES-256 cipher. So these options are also supported now. In terms of performance improvements, if you look at it, Seek is one of the most expensive call in the earlier implementation of S3A file system. So whenever you have a Seek, what used to happen is that it breaks the existing connection with S3A, reestablishes the HTTPS connection, and reopens the file and lands up on a specific place or location. So that's a lot more expensive call because, as you know, re-establishment of the HTTPS connection is a lot more expensive. Just to give it in perspective, it's as expensive as reading some 300 to 400 KB of data from S3, right? So the problem gets more pronounced the moment you have something like a positional read, where the read doesn't change the offset within the file. So what I mean by that is, positional read is internally implemented as seek followed by a read followed by seek. So you seek to a specific location, read a set of bytes, and then seek back to the original location. So there are two seeks involved, and the earlier implementation, it's going to abort 2 times, the connections 2 times. And any input formats which are going to make use of this particular API is going to suffer a lot in S3 as compared to the earlier implementations of HDFS and so on, right? So in the recent implementations, we have fixed this problem where we made seek as a no-op call, and we reopen the file only on need basis. That reduced the number of connection abort problems by almost 50%. And the second problem that we had was with respect to the backward seek. So some file input formats like be it ORC or be it Parquet, they have initially they read the data which is located at the end of the file. So basically they read the footer information first and then head back to the beginning of the file in terms of reading the realistic block details. That becomes a lot more expensive because the moment you do a backward seek, the connection was getting terminated. So in the recent versions, we have fixed this problem where we introduced a effort-wise variable which can be set to random mode or in sequential mode. The moment you set it to random mode, we are going to exactly request for the amount of bytes that we are going to read from S3, thereby reducing the number of connection aborts. Let's look at a application like Hive, which is built on top of this layer, and try to understand how it impacts the performance. So if you realistically look at the at a very, very high level, the kind of access patterns that are going to be in Hive are the ETL or the admin related activities, where you bring in the data from the external sources, create tables, analyze the tables, or do some transformations so that it can be exposed to the end users, or it could be computing the column stats, or if you have lots of partitions, you might end up running some tools like or commands like MSCK and so on. Basically the admin related activities. Once the data is exposed to the end user, they're going to run a set of queries in terms of mining the data, and they might end up writing the data onto some specific location. Even the ETL data can write the data onto some location, basically the read and the write access patterns. So if you already have the data in S3, you would end up creating an external table in Hive in terms of exposing the data to the end users. And if the data set is already partitioned, the partition related information will not be directly populated onto the metastore automatically. So you have to run a tool like MSCK, which is again provided in Hive itself, in terms of populating or scanning the directory within the table, and it's going to populate the metastore information one at a time. So the reason why this can be expensive is that if you have, let's say, some 1,000 partitions, it's going to scan each one of the file in a sequential fashion and then update the metastore. That's going to be a lot more expensive call. In the recent versions, we have fixed this problem where we reduce the number of calls to the metastore as well as parallelize this particular activity, and got almost like 3x improvement in terms of the response time. For a Hive query to execute in a lot more efficient way, it's extremely important to have the accurate table as well as the column level statistics, right? So you can pretty much gather the table statistics in an automated way by turning on Hive autostats gather equal to true. But in order to compute the column statistics, you'll have to run an explicit command like analyze table, compute column statistics for whenever you update the data set, right? And that turned out to be a lot more expensive call because of the number of calls to the metastore. In the recent versions, we have fixed this problem and saw almost like 3x improvement in terms of the response time. The reason why these things are important are that, as I mentioned earlier, if you have to spin up a ephemeral cluster, you would want to bring up the data or bring in the data from the external sources as quickly as possible and be able to expose the data onto the end users and let them complete the query as fast as possible. Then only you'll be able to make the best utilization of the cluster. So that's one of the reasons why we concentrated on all these areas. So in terms of other performance considerations, if you look at the way that the Hive queries work, the moment you submit the query, the first and foremost thing that's going to happen is the split generation. And if you have lots of data to be processed, the split generation itself might take a lot of time. So certain file formats like ORC and Parquet, they support a set of thread pools which can be made use of in terms of computing the split generation. So it provides, or Hive at a higher level, it provides a set of files to be scanned, and these threads can be made use of in terms of communicating with the S3 and then get the information. So you might want to tune or set the appropriate number of ORC, thread pool based on your use cases. And ORC also has different split strategies. For instance, it supports ETL strategy, it supports BA strategy, it supports hybrid mode, and so on. The moment you choose the ETL strategy, it's going to read the footer information first for doing some of the split pruning activity, right? And that can turn out to be a lot more expensive. The reason is it's going to read the footer information from S3 at the time of split generation itself. The good news is that it will be able to cache all those details onto the local JVM itself. So when you run the or similar query or like the same query again, it's going to be a lot more faster because it's not going to read the data from S3 and it will be able to look it up from the local cache itself. This will be a lot more useful in scenarios where you, let's say you have 1 year data of 1 year worth of data to be analyzed and gradually narrow it down to 1 month. So the first 1 year worth of data is going to be a little expensive because it has to read the footer information from S3. But the moment it is available in cache, the rest of the queries are going to be basically fast, right? And once the split generation is computed, the second thing that happens is setting the number of tasks and letting the task proceed, right? So the split information is given on to the task side, and the task reads the files in terms of computing the query or so, or performing the query or so. And at the time of what happens in the case of task side is that the moment it receives the split load, it reads the footer information of the ORC again, because it needs to read the details so that it will be able to locate the data blocks. So the data is read again in the task side for understanding the footer information. Ideally, just now we read the footer details in the app master side. So what could have been done is that you could have passed on that particular footer details along with the split payload onto the task side itself. So that optimization has been made, and it was available earlier itself, but it was occupying a lot more memory in the AM side. So those problems have been fixed now. So that helps in terms of reducing the number of S3 reads in the task side. And Hive uses Thais as its default execution engine, and Thais, or like the moment split information is computed in Hive side, it gives it on to Thais for doing further optimization. And Thais does a lot of activities based on the number of min-max split groups that you have got, the location details, and so on. The interesting observation is that S3 always provides localhost as its location information. So if you have a very small table, Thais is going to aggressively optimize and provide only one task. So that's going to be a problem, because let's take an example of an item table in TPCDS dataset, which has got some 52 files, right? So if it is less than a min threshold, what's going to happen is Thais will aggressively optimize it and provide only one task. And that task is going to open up all the 52 files in a sequential fashion and then decode the data within that. So that's going to be a lot more expensive operation. So in the recent versions, this problem has been fixed, where Thais doesn't aggressively optimize if it doesn't know about the location details in advance, or enough details about the location details. And we also observed that in AWS, the container launches were slow when we used capacity scheduler. So that problem has been addressed the moment we realized that, hey, AWS doesn't support any of the rack locality and so on. So we can turn off the node locality delay to 0, and that helps in terms of speeding up the container launch rates. With all these things in place, we ran Hive test bench, which is a subset of TPCDS queries, and we used 200 GB scale in TPCDS, and the data was stored in S3. We used M4 4x large nodes, which are like general purpose nodes. We had some 5 nodes in place, and we compared with the previous version of HTTP with the latest one on the cloud. Interesting observation is that lots of queries, like query number 15, 17, and so on, they didn't even run in the early versions of HTTP. The reason was AWS connect timeouts were happening. But with the recent versions, this has been fixed. All the queries run, and also we get an average speed up of 2.5x. If you want to speed up the queries a lot more faster, then you can make use of Hive on LLAP, which is in tech preview mode. So it provides a lot more performance, where it reduces the amount of read from S3, and we have seen almost like 4x improvement in terms of the performance. In terms of best practices, if you have large volume of data, you might want to tune the multipart setting, which helps in terms of chunking up the data on the local environment and uploads the data in parallel fashion. And if you're using capacity scheduler, you might want to turn off the node locality delay. And if you're using Hive, you might want to turn off the storage-based handlers and so on, or storage-based authorization provider. And if you have really large data set, you might want to tune the number of ORC threads that are available. So with that, I'm pretty much done with the talk. So open for Q&A.
Actually, we've run out of time, I'm afraid, for Q&A. So yes.
Okay.
So yeah, maybe you can take it offline. If that's
Sure.
okay, yeah.
Thank you.
Quick couple of announcements about cars that need to be moved. So, in addition to the earlier announcement about a car that needs to be moved, the following vehicles are blocking someone else's car. They are number plates KA51ME2191. I'll repeat that. That's KA51ME2191. The next car is KA53M4541. That's KA53M4541. If either of these cars is yours, could you please move it or speak to registration desk?
Hello. Pardon?
Warning bell
Yeah, told 10 minutes.
before 10 minutes. Possible to pull this? Oh no, I think it's.
So we don't have a break right now. The next speaker is going to start soon. Before that, a quick announcement about goodies. So mugs are being handed out. If anyone wants mugs, eVive Health is giving away mugs. You can collect them from the registration desk. All right, thank you. On to the next talk.
Start.
Guys, could you please settle in quickly? The speaker is waiting to start.
Good afternoon. My name is Anindya Shankar Dey and I work for Walmart at Walmart Labs here. And as the title suggests, I'll be talking about how at Walmart we are using machine learning for solving various business problems with a deep dive into our automated self-learning forecasting system. Walmart is the largest retailer. We are present in 28 countries with approximately 11,500 stores, with 5,000 stores in US alone, having greater than 260 million transactions every week, creating petabytes of data every week, which we need to process and make our business decisions. Our founder Sam Walton once said, exceed your customers' expectation. If you do, they will come back over and over. Give them what they want and a little more. And we are following the same footstep using machine learning. We are finding out what our customers really want. We have millions of customers, and so if we try to find out what each and every customer wants, we will have variety of data because every customer's perspective differs from one another. But to find out collectively what our customers really want, we have to go back and process the data we collect on a daily basis to find out what they want. So giving some examples how we are using machine learning and why we are using machine learning. Walmart is a retailer shop. In this world of e-commerce, we still have physical stores. And using machine learning, we are able to find out which market, which city there is a need among the customers for us to open a new store. In the earlier times of Sam Walton, when we wanted to open a new store in any particular location, he used to go on a flight, and from the aerial vantage point that he had, he used to decide where is the optimal location to open a store. But in this digital era, we have data to facilitate that, and we have built a system which on demand, when we require it, it gives us back using machine learning that this is the market where there is a need for you to go and open a store. And at this exact location, if you open a store, it will be helpful for Walmart as well as its customers. Not only on real estate, we have a huge presence, or a huge machine learning happens at the customer perspective as well, especially on the omni-channel mapping. We have the capability on a real-time basis. Whenever a customer transacts in our offline stores, if he has an account with Walmart.com, Immediately after his transaction at the store, within a few seconds, we can map his online profile without knowing anything. You can be a random customer. You just go into a Walmart store and do a transaction, and you have a Walmart.com account as well. We have the capability to match you back with your Walmart.com account, which will help you from a customer's experience point of view, when you go in a Walmart.com site and see your past order, you see not only your online orders, but your offline orders as well, giving a much more holistic experience. Not only we have talked about the physical stores, the customers, and now on the merchandising, which people actually come to buy at Walmart, where machine learning is happening day in and day out. We have system design which tracks what products are available in the market, what Walmart is carrying, what Walmart is not carrying, and then deciding which is the best item that Walmart is currently not carrying and he can carry. So our system gives this recommendation to our buyers. We also kind of find out if a product is not there, is not available, which is the product that is the most suitable substitution and is wanted by the customers. The system recommends them as well. Now, Walmart is not an OEM. We does not manufacture anything. We sell products created by OEMs, and for that our logistic operation is another huge part. Our supply chain is one of the largest supply chain across, and machine learning over there is used at the severest form. Demand forecasting is one of our most critical work, where we focus what will be the what will be the amount of demand for a particular item at a particular store for the next few weeks, which I will go in details after this. We find out we have developed systems which tell us if a particular supplier will not give a product on time, there will be a delay in its lead time, so that the stores can prepare alternate products for that point of time. And as we know, we have ventured into delivering to the customer's home, where we are using machine learning in a huge way to find out the optimal route and optimal way to deliver our product directly to the customer's home so that they can live better. Now, we use standard machine learning algorithms like deep learning. We use graph theory quite a lot. We use clustering. We use optimization techniques like genetic algorithm and many more. And more than that, more than often, we use home-written algorithms. We have scenarios where standard algorithms does not work. We go back to the whiteboard, do theoretical research, and build our own proprietary models. Now, the main part of this talk is our forecasting system. Now, before we go into forecasting system, let me talk about traditional machine learning, when machine starts to learn on its own. Whenever we talk of traditional machine learning, be it as complex as image processing, facial recognition, any kind of pattern recognition as a whole, or natural language processing, where we evaluate our natural languages and make computer understand what we speak collectively. Or if we try to build a system that just distinguishes between two type of customers or anything. This is where the traditional machine learning usually revolves around. But there is one thing, from the very complex image processing to just a distinguishing algorithm, is all of them are classification systems. We have our data in place which has labels, and we train an algorithm that will be able to classify a new data into those very labels. We do not talk about usually about building a system, building a machine that can forecast the future. We do not talk about forecasting systems. And there's a reason. It's much more complex than a classification system. Just even if you consider very few items in Walmart and check their sales pattern across the weeks, you will see multiple and multiple varieties of patterns emerging. And it's hard to build a system that will classify all those systems at once. Even if you just take one item which have a smooth time series framework, we have to distinguish and have to estimate its trend component separately, its cyclical component separately, seasonality separately, take care of the irregularity part, find out if it's affected by outside model, and then find which is the best model to give, for this time series to be forecasted. And then only we get the forecast results. So more than often, forecasting one time series becomes a huge job, becomes a project. Now imagine, we have 5,000 stores in US and every store carries 1 million items at least. So what are we talking about here is building a system that will do time series forecasting for each of those 5,000 into a million items, and not just time series forecasting, it will do the forecasting by finding out the best model for each and every time series, for all of them, at parallel. The project started with our requirement of the reduction of buffer inventory. So that we do not go out of stock, we often have buffer inventories in our stores, so that when there is a huge spike in demand, we are able to meet that. But it doesn't happen always that way. It's not always good to create lots and lots of buffer inventory. If we have inventory which is not getting sold, it's actually taking up shelf space of items that the customer wants, and we are not able to meet the customer demands because we have inventory of an item which is not getting sold. So we needed to build algorithms that do store item level accurate forecasting as much as possible. And for this reason, we collected various internal and external data for building our forecasting algorithms. Now, people familiar with time series might know that even if you just take the historical sales value of the time series or historical data points of time series using univariate models, it is possible to build good time series models. But consider this scenario. Suppose a particular item, snow shovel. Everyone knows that gets sold mostly in the winter season, and there is a smooth seasonality for sale of snow shovels at that time frame. And univariate time series can predict that. But suppose there is a snowstorm warning that has been given in a particular region. If there is a snowstorm coming, people will flock to our Walmart stores to buy snow shovels, and that will be a huge spike in demand, which will lead to an unexpected sale of snow shovels, which our univariate time series model will not be able to capture. And that is something we try to incorporate into our current system. So we collect various internal and external data sources. We create multiple time series models on top of them. We build our hardware and software capability so that we scale up at a Walmart scale and then choose the best model for each store item combination. I'll be going into deep dive of the architecture after this, but this is where I want to focus on. We doesn't just fit one time series model for each store item combination. For each store item combination, 5,000 into a million item, for each of them, we have a system that builds multiple models and find the optimal model for each of them and then does the forecasting. And I'll explain to you why I have called this system a self-learning system in the architecture part of it. So, as start of any machine learning process, the first step where we start is the data gathering process. So we collect various data from internal and external sources using web crawlers, where we mostly use Python for web crawling, and our database we have is Hadoop. The processing in Hadoop, we mostly use Hive, and the statistical processing, we mostly use R. Now, once we have all the data, we go into our feature engineering and selections. So we create various features from our data itself. And then we have built an algorithm which automatically selects for this store item combination, these are the features that needs to be included in the model. And these features are not only collected, not only based on the data we have collected, note this in mind, I will come back to this. We also convert our time series into features. There are ways to extract information from the time series data as well and make them non-time series features as well. So once we have this, we build various forecasting models, some of them like dynamic linear model, ARIMA with Fourier seasonality, and in this system we have lots of home-written algorithms as well. Now when the system was initially deployed, how the system used to work, for every store item combination, it used to create multiple models, and then based on the history it has, it used to choose which is the best model for each time series, and do the forecast. I'm not talking about the ensembling part because that's where the self-learning mechanism comes up. Now, once the system was initially deployed, once we find which is the best model, the system used to go and collect the actual data when the time comes and does various kind of model validation and analysis. So the system was analyzing that I have forecasted for the next few weeks, these are the values for this store item combination, and this has actually happened. So we have written algorithms in place which go back and find out, okay, the forecast was good during this week when these are the variables were involved. The forecast has gone down now. So might be these are the things that needs to be there which is not there right now. And it creates feedback for itself, which goes back into the system in the next run. So not only just, so this keeps on updating itself, this feedbacks goes back in the system saying, okay, we have seen that these variables is not getting picked up by our current model selection algorithms, but it is important for this store item combination. So whatever happens, we should be talking about it. We should be getting that variable into the system. This is one part where self-learning works. The other part where the system is self-learning is, at this point of time, we have historical data at what time point, what was the best model. And what we are doing now is we are ensembling various models we created, and the weights keeps on updating itself. We decide based on the historical data which was the best model, when a model is usually performs the better, and the weights are continuously self-learning to based on the various features we have created, various time point based on the historical based models. Like, so suppose we have 5 models, we have W1, W2, W3, W4, W5, and historically the first model at a particular time point is better. So the model gives higher time point when a similar situation arrives. As I explained earlier about the snow shovel part, if a model is very good at predicting snow shovel, that model will always get better weight for predicting in the ensembling part of it. Also, we can have the capability now to predict what so as I mentioned earlier, we have the best models and we have created our time series features from our time series. So we can actually predict which will be the best model and use that prediction probability as our ensembling part. So this is how the entire system works, and as we go on and on, the system has stabilized and we are able to create better and better forecasts as the process go on. So this is what we have on the forecasting system architecture, and this is, I am open to questions actually.
Hello, interesting talk. So I have a question. In the initial slides, you had mentioned about the mapping of the offline, data with the online data, right? So how exactly does that work out for random customer UI?
That's a long process, and I think it's better if you come back to the Walmart booth. There are people who can give some guidance on that.
Okay.
So that's an entirely different system altogether.
Any gist you can give of the?
So we can match the names, and sometimes they provide names and all on the POS stock, and we have capability of matching the closest match, and we have been very much able to find out the closest match to these things.
Thank you.
Hey, I have a question about the validation part that you showed. What are the exact matrices that you, or the metrics that you validate on? Like you said that we compare with the original sales, but what are these, like MAPE or
yes, so
what are the other things?
We have decided we use MAPE. We also find out, we take MAPE at various instances like 3-week MAPE, 12 weeks MAPE, on the various forecasting depending on, and also something called hit miss kind of scenario. So how close was the forecast? Like was it very close? Because MAPE is an average, so we also take the count of closeness to the model, to the actual forecast.
Hi, I'm Vikash, and I have questions like so for different departments, you build different things. Like for suppose in a city for a store, you have a model forecasting some X things for X items, Y items. Then this has to be gone to some warehouse where the supply guys will have their own models or any other stuffs going on. And then how do you integrate it to the complete supply chain and get a feedback that okay, it was not given back, and what we have said has not been done. So how this integration happens with all other departments together for a smooth flow of products into the store?
So as I said, we do the forecasting at store item level. Now this goes back into our order management system where we have dedicated buyers and the logistic person who takes care of that part of it. So what we give them is what will be the forecast changes, and then people there are people who take these forecast values and decide on what to do next.
Hi, I just need to quickly interrupt. You can continue with the Q&A.
Yeah.
There's like an urgent announcement about cars blocking
Sure.
other cars. So KA05 MK8054, that's blocking another car. KA04 N3424 is blocking another car. And KA03 MV1162. So if any of these cars belong to you, please talk to registration desk. Once again, KA05 MK8054, KA04 N3424, KA03 MV1162. You can continue with the Q&A.
Hi. So I had a question on products which do not have history. I have a question on products which do not have history. Let's say you have a television, but for a different brand, and this is completely new. So how do you forecast in such cases?
I didn't get the question.
So let's say you have a television from a completely new player, like this Leak or something which recently launched in India. I'm taking India's case so that you understand. I don't have history for that brand and so on. So how do you model the time series for that?
So for very new items, we have a separate system in place which takes care of similarly selling products and uses that approximate those kind of models to approximate what will be the sale of this product. Because if for any new product introduction, there will be a different hierarchy. It will be like a Gomper's curve, right? So the entire modeling architecture for new products is different. We do not classify new product in this system.
On just the model, or is it on the features of the product as well? Is it on the brand, or is it on the features of the product? Both.
So depends. So as I told, this system is not designed for new products. So that's a totally different system that's in place that works out over there.
I have a question. If certain factors are affecting a product, and if some factor suddenly drops down or suddenly jumps up, then how that impact analysis? Impact of that variable will completely deviate your model. Then how will you factor that? How will you decrease its effect on the overall model?
So before even going into the modeling section, all the data pre-processing like outlier detection and all of that usually happens. So if such a scenario is happening, we are smoothing that out. So.
But it is good to completely remove that data point, or we have to.
Depends. So if it goes beyond thresholds, then we have to completely remove that. Otherwise, we can still smooth it out and use it.
Okay.
Hello. Hey, I have a question. You talked about history-based model selection. So is it that you are running, let's say, 5 different models parallelly throughout the year, and when, let's say, winter comes this year, you just pick the model that ran best last winter? Is it like that, or did I misunderstood?
Lot of that. So not only what has happened in the past, like at this point this model was the best, but we have designed a system that we can actually predict what will be the best model right now. So we can use those probabilities as well.
So you predict what's going to perform the
What's
best?
going to the best model at this point of time, yes.
Okay, what methodologies do you use to predict that?
Pardon?
What methodologies do you
classification.
Classify.
That's classification.
Okay.
Okay, thank you.
Thank you. So guys, you can take your questions offline. We have a lot of time. The next talk starts only at 5 o'clock. Okay, sorry, that's been cancelled. 4:45. Sorry, I just got a conflicting request. The schedules have been quite difficult to handle today because of traffic chaos in the morning and various other things. So I have a slightly different, less serious announcement. There's a Spark workshop on 3rd August, Wednesday, at ThoughtWorks office in Bangalore between 5:30 and 9 p.m. So this is a Spark workshop. It's a technical workshop on 3rd August, that's Wednesday, at the ThoughtWorks office in Bangalore between 5:30 and 9 p.m. To register yourself, talk to the ThoughtWorks booth in the lobby. Now's a good time to go check if your car is blocking anyone. So take a break, come back. We'll see you at 4:45. Hi guys, just a quick one. If you're running hotspots, it would be good if you put them off because they're making things worse for everybody else. We're getting a lot of interference on the channels, so if you're running hotspots, bear with us, and we have to cooperate on the wireless because we're sharing wireless channels, and they're fixed channels, and the admin is complaining, and his name is Trouble, so he will make trouble. We'll be starting at 4:45, quarter to 5. And in between, I'll keep running a couple of announcements. If you have excess food tokens, you could exchange the value on them for credit on buying t-shirts at the registration desk. If you don't want discounts, do please return them anyway. If you've filled up the feedback forms, please don't forget to drop them in the box at the reception area. Your feedback is very, very valuable to us. So if you haven't got a form, grab one of us, or if we're distributing them, please collect it from us. Just raise your hands as we come along with the forms. Thank you. Hi again. So for people who missed this announcement about a free workshop, there's a Spark workshop on 3rd August. That's Wednesday at ThoughtWorks office in Bangalore between 5:30 and 9 p.m. To register, you talk to the ThoughtWorks booth in the registration area. Regular reminders about turning mobile phones quiet and taking calls outside. The emergency exit is the back to my left. Next talk starts at 4:45. And the one after that will be immediately after at 5:05. And then we break out at 5:35. We're done. Once again, if you haven't returned your feedback forms, do please fill them in and return them. And Q&A, try to grab a microphone. We're short of time, so first come, first serve. We're sorry we haven't been able to give you a countdown on the number of questions left, because things have been quite chaotic today, but do expect that you may be losing the opportunity to go online with your questions, but the speakers are always around for you to ask questions offline. So yeah, just remember that questions on mic are better for people who watch the talk later on online. All right, thank you.
Hello. Hello. Yeah. Thank you, Hasgik. Thank you, organizers and volunteers for having me here. Good evening, everybody. Yeah. Let's try once more. Good evening, everybody. Awesome. So, I'm Rohit. I work at Ola, and today I'm going to share our experience of setting up a centralized logging platform. We do something which we do it at Ola scale, billion plus messages and 100K requests per second. So what is Greylog? Greylog is a log management software that actually works. It has lots of features like search, analysis, alerting, pipelines, and a lot more we'll see later. Now, before we look into this, how many of you are Ola users? Well, a good show of hands. So that basically explains we have volume. So Ola logging requirements is because all of you are using it. We have a huge volume, billion plus messages per day. And since all of you are simultaneously booking cabs, we have velocity. And internally, Ola is powered by a lot of microservices. So we have hundreds of applications which are pumping logs at the same time. And each of their application, all the applications may not log exactly the same way. They may have their own requirements. So we have a variety. which category. So this is basically a typical big data statement. Okay, how many of you heard about ELK? A lot of you. ELK is a very popular stack and very widely used for log management. Even at Ola, we used to use ELK a lot. But we found that it is a bit maintenance intensive. And we often end up building on top of it. So we wanted something simpler, something which already has logging capabilities, something which doesn't require day-to-day maintenance. So we were looking for an alternative. And we found Graylog. But why Graylog? First of all, if you look at the name, the Graylog itself has the word log. It is designed for logging. It is designed for solving just one problem, which is catered towards logging. All its features are towards logging and not anything else. While in case of ELK, it may be used for other things as well. It is a generic platform. Some of the features is a beautiful UI which can be used for log searching. You can also see on the top right the throughput which was at that moment. We can search based, in our case we are searching based on application. I don't think that is visible. We can have beautiful dashboards. In this case, the dashboard is for an application called Heka. And the message trend for the last 1 day is being shown over here. Then there's a message count for 1 day. The cardinality as the number of unique messages. It's a quick values is a pie chart with showing the messages which occur most frequently, like the top one which is occurred 3.28%. This is a small application, so it is not logging heavily. Okay, Graylog is again powered by Elasticsearch. It uses Elasticsearch to store all its data and query the results. The good thing about Graylog is that you can manage everything, manage all the Elasticsearch indices from the UI itself. And it gives you a lot of flexibility to manage indices based on time, message size, or even the message count. So this is a sample configuration in which each of the index is of 40 million, can store 40 million max records, and 250 of them can be present at any point of time. So this is basically a configuration for storing 10 billion records. Several input and output options. Graylog has pipeline support, and just like it can take messages from a variety of sources. In this example, you can see I've just searched Kafka, and there are 3 different modes of taking input from Kafka. We can take input from syslog, from TCP. There are other options as well, like RabbitMQ. Again, output can also be a variety of different plugins. There are some of the plugins are built in the Graylog itself. Some are community supported. Some you can also write your own. Real-time log analysis and reporting. So we can create streams based on some criteria. For example, an application name can be a criteria. We can create alerts on streams. So as we are getting the data for that application, we might grab some particular line and trigger a PagerDuty if that is of importance, or maybe on message count. So there can be a variety of real-time log analysis and alerting. Now, it's from the feature wise, it looks very good. We did a POC and we had a journey. Few months back, we started exploring the alternative. We came up with a pipeline, and we thought it was great, but we ran into a lot of problems and learnings, which I'm going to share today. So this was the initial pipeline. So we tested it on staging. It worked fine. Docker is powering most of our microservices. There are tons of microservices. And all the applications are logging to standard out, which can be cached by a Docker logging driver. We are using a Fluentd log driver instead of the default one, which writes into file. This in turn is sending the traffic to Fluentd on a TCP port. Fluentd is a data collector. It can collect data from a variety of sources as you configure it. It can process it in real time and send it to various destinations. Over here, we are using Fluentd as a dumb box. It will just receive the input in TCP and forward the message to Kafka. Why not directly to Kafka? Because a Kafka logging driver doesn't exist for Docker. If that existed, probably we would have used that. Kafka is a publish subscribe system. Fluentd is writing the messages to one of its topic. Any number of applications can write to a topic at any point of time, and there can be a number of applications consuming from it. So Kafka is receiving the messages, and you have to subscribe to the messages. So we have another Fluentd which is subscribing the messages from Kafka, then formatting it in a GELF format, Graylog extended log format, before sending it to Graylog in a UDP port, because we believed network would be reliable and UDP is fast. Graylog had two components, Graylog server and web server. The Graylog server has all the functionality, while Graylog web server is just a wrapper on top of Graylog server, which will call the REST APIs to show the UI. And Elasticsearch is used for storing the messages. Now, our first problem happened. The Fluentd container consuming was dead slow. But we believed it is sending the messages to UDP, it should be fast, and it was consuming from Kafka in real time. So Fluentd should not have any problem. What we did, we upgraded all the versions for different components. As you see in Graylog, now the two components is merged into one. That is in the new version, we got this upgrade. We tried out beta, REST API and UI is in the same box. But the problem is still not solved. The problem was at the Fluentd GELF plugin. So this was slow. What we did, in the new version of Graylog, we saw that it already has a Kafka support. We started formatting the messages at the source itself before sending it to Kafka in a GELF format. And Graylog is able to collect the messages from Kafka and also index it very well. So the first problem case solved. What could go wrong next? Our Docker processes daemons started crashing. We used to get PagerDuty that in a production box, Docker daemon crashed, and when Docker daemon crashed, all the containers will crash. Why? Because of the simple reason, we onboarded few more applications, and it was logging at huge. It was logging heavily, and the buffer of Fluentd was full. So it crashed. But why should a Docker daemon crash? Because of something less important like logging. So we thought probably we should upgrade. We did upgrade we read some articles, we upgraded to latest version of Docker. We also read few articles which suggested upgrade the kernel to 4.2. We did all that, but now instead of crashing after say every 4 hours, it was crashing at every 5 hours. But the problem is still not solved. Yeah, so forget the fancy terms. Don't use the Fluentd log driver. Use native log driver, which writes to file in the JSON format, JSON file log driver. And we will use tail plugin in Fluentd to tail the files and then send it to the pipeline. So this was the solution. I've just removed that component because it is now independent. So it will stream all the logs by reading from the files. It automatically detects the new files when new containers are created, and the pipeline goes well. We are happy. Again, we got into another problem, huge log messages. Now, any idea what could go wrong when we receive such huge messages? Elasticsearch indices are powered by Lucene, which supports a max of 32 KB. I saw a message which was 3 MB, a single message. Of course, it will raise a exception, and Greylog will try to send the message again and again 5 times before finally discarding the message. And Greylog will not send the other messages until this message is either sent successfully or discarded. So there's a huge lag. Solution: either truncate the message or divide it into multiple parts. We decided we'll just truncate the message. We came up with 8 KB as the max field size, which the JSON will support. And the problem is solved, because exceptions will not happen if the message size is. Number 4. Now our platform is kind of popular. More developers are interested in onboarding their application to Greylog, but they are not into the traditional. They are not into the modern Docker platform. They are running it on the system, like the box. So their application is generating the messages in JSON format in the files. We need to tail the files and send it to the pipeline. So that's what we did. New apps onboarded, which were not on Docker. Now what happened? Some of the applications may have similar keys, like for example status as success or true. It can also be an integer as 1. What happens that this detail is sent to Kafka, Greylog, and finally it reaches Elasticsearch. The first time it comes to Elasticsearch, Elasticsearch maps the data type, associates a data type with this field. If the field is if the first message received is status equals to true, it will map it as Boolean. The next message comes as success, it will throw an exception. That was happening. So what we did, the logic is simple. At Fluentd level, since we are powered by like hundreds of microservices, different teams sending the details to us, we wanted to solve it at our end. So what we did, convert everything to string before sending it to the pipeline. Since all the data types are string, it will not throw an exception. Now, we had many components, but we realized that we are using buffer at each level. So whenever some problem happens, we have to look at each of the component. Where is the lag? There can be lag at the first component, second or third. Is buffer at each level necessary? We found the answer is no. The first one, Fluentd, is actually tailing the log files, so the file can act as a buffer. We have Kafka as we want Kafka to have the storage to store the data for two days, so it acts as a buffer. At Greylog, we can throttle the input to match the output. So Greylog, it's not necessary. It can always replay the message from Kafka. It is not needed. The final problem. Fluentd is tailing the files, sending to Kafka, but we experienced message loss and sometimes delay. Why? Because the Fluentd Kafka plugin was not fast enough. It was written in Ruby, and it was designed to be simple but not performant. Adding more CPU and RAM will not help. So what we searched for an alternative. Luckily, we found a project called Heka. It is a Mozilla sponsored project, and Heka is written in Go, very performant. What we experienced that it can do all the things which Fluentd can do, plus it has more features but complicated. So with Heka we saw we are now 10x CPU friendly, 5x memory friendly, Now, finally, who, all said and done, who liked it? Developers, because we have a centralized we have user authentication. They can log into they can check the logs directly. They can do quick RCS debugging in staging as well as production. We can sleep for some more time, and the management can see beautiful dashboards, get more insights and visibility. You can also try it yourself. This is something which I did a few hours back. I uploaded a Greylog Docker image. You can just run these three commands. You'll have a Greylog setup ready to use. I think that's it. I'll just explain one more thing, that is the Kafka layer. The reason why Kafka exists is because with Kafka we can take another pipeline and use it for long-time archival purpose. Like Secor, we are using Secor for pushing the messages to S3 at the same time, while Greylog will have the messages for, say, 7 days. Yeah, I think we should open up for Q&A.
Hi. So, looks like you pretty much replaced L and K of ELK stack with the Greylog server.
Right.
So, what were the main benefits that you got out of removing? Because it seems like you're pretty much doing the same thing.
Yeah.
So, what was the benefit? And in my experience, most of the problems that happens is because of Elasticsearch.
That's correct. So, the main advantage of having Greylog is that you get everything at a central place. When you're using ELK, you often end up building on top of it. Like you will be configuring the Logstash shipper with, you will be writing all those configurations. You will be using Kibana for viewing the logs. You get all those features at a central place. That is the biggest benefit. And of course, it has tons of other features.
I mean, what is the feature? That's what I was looking for.
The feature like streaming support.
The ELK, I think Logstash has that support.
So it is similar. The basic idea is when
I understand it's an alternative, but is there anything major benefit that you derived out of it which was not there in ELK?
The major benefit is that today I want to manage Elasticsearch based on message count. Tomorrow I may want to use it based on time, and all of those I can do it with a single click of a button. That is the major benefit I've experienced. Second is that with ELK, we will be building on top of it to actually make a mini Greylog. So Logstash shipper and RabbitMQ, all those come into picture. And over here, Greylog comes into picture. From the CPU cycles perspective, it will be similar. And we found this as a better alternative. ELK can also do the similar things.
Hello. Yeah. So I have a question. There is actually a Gelp driver from Docker itself. So have you tried that?
Right.
I mean, it also has the same problem of buffer which you had with Fluent driver.
No, actually, we wanted Kafka to be in between.
Okay.
Okay. So if it had Gelp Kafka plugin, we would have probably used that. We tried out that. It works beautifully. It can send messages directly to the Greylog server.
So there's no buffer issue which you had with Fluent.
It sends. We were using it with UDP. So UDP, if the buffer, there's no problem with buffer, right? If the destination is not receiving the messages will be lost.
Okay.
TCP is also there, but I think UDP is more used than TCP.
Hello. I'm afraid that's all we have time for now. Okay. The next speaker will have to get on. So you can take your questions offline.
Thank you.
While she sets up, how many of you know where the name Fifth Elephant came from? Anybody? The book, yeah. It's the book by Terry Pratchett on Discworld, which is a world that's held up by 4 elephants on the back of a turtle. I just looked that up on Wikipedia right now. Good work.
Hello? Okay. Thanks. Hello? Hello? Is it clear? Because, hello? Okay, hello, yeah. Oh, yeah. Yeah. Um, yeah, it's on, right? Um, Hi, good evening. My name is Aruna, and I work as an astronaut at Mapbox, really. But what I do is engineer, and I look at the world's data every single day. And today I want to talk a little bit about having a conversation. I want to say, let's analyze the world in the time taken for you to enjoy a cup of chai, either on your own or with someone else. Or as a developer, should I say, let's parse the world over a cup of chai. Or more specifically, what I mean to say is that let's extract, filter, analyze about 5 billion uploaded GPS points, about 3 billion nodes, about 362 million ways, in about 16 minutes on a very expensive machine like the Amazon EC2, or in about 25 minutes in a less expensive but still expensive machine like the MacBook Pro. And to make this more enticing, we will be doing this with JavaScript, or more specifically, with Node.js. The world that I know very intimately, the world that I work very closely with as a developer at Mapbox, is the world of OpenStreetMap, which is the largest living map in the world. OpenStreetMap, in all likelihood, contains the house that you grew in, the parks that you played in, the train stations you got off at. You get the drift. But more importantly, OpenStreetMap gives you the freedom to add your own unique perspective of the world to the map, and even more importantly, it makes this data freely available for anybody to use, to parse, create, and build with. In short, OpenStreetMap is yours to keep, grow, and cherish. Before chai though, let us have some introductions to the earth, but as data. The earth is a staggering data set. Let's take a moment to think about everything that we've seen throughout our lifetimes, right? The sheer diversity of the objects, both natural and man-made, that we've had the fortune to look at. You'll be surprised to know that all these objects, in all their diversity and all their entirety, can be represented by 3 simple geometries, which are points, line strings, and polygons. There's also another concept of relations, which I'm going to be ignoring for the duration of my talk, but I'm happy to answer any questions on. Some examples of points are mountain peaks, trees. Some examples of line strings are rivers, roads. And some examples of polygons are buildings, lakes, and fields. But how does this data really look to the computer? So when the computer is seeing a point, it's seeing an image like this, or more importantly, it's seeing this JSON structure on the right. I'm going to take some time to break down this JSON structure for you, because it is important for the rest of my talk. So this JSON structure is usually of a type feature collection, which is a collection of the Earth's features. And these features are usually an array of objects. And this is how a feature looks for a point. So it's got a type feature, it's got some properties which are metadata, and it's got a geometry which contains again a type called point, and it also contains some coordinates. A line string looks very similar to a point, except that here the geometry is of a type line string, and you have more coordinates than you would in a point. A polygon looks very similar to a line string, but it's got even more points, and The first point and the last point are the same. I spoke a little bit earlier about metadata. So metadata is basically any data that you want to associate with a feature, but that's not related to its geometry. So on OpenStreetMap, this could typically be the name of the person who edited that feature last. It could have the timestamp of when that feature was edited. But more importantly, you can have visual metadata. You could associate properties like color, size, opacity with this data. This is a map of Toronto where we have visualized several points of pedestrian accidents. And you'll see that these circles are varying in size. Some of these circles are bigger, some are smaller, some are red, some are yellow. And all of this denotes the intensity of the accidents, the number of accidents that occurred, and so on and so forth. Before I move on to the core of my talk, I want to spend some time talking about web maps. This is not directly related to how we're going to parse or process geospatial data, but it contains a really elegant concept about how geospatial data can be broken down into very logical chunks. A web map contains many perspectives of the world. It contains a perspective of the world as the moon sees it or as the satellites see it. It contains a perspective of the world like the birds see it. And it also contains a perspective of the world like you and me see it. And the reason why this is possible is because of the property of zoom. Now, as we zoom in to this map of the United States, you will notice that as you go deeper and deeper, there are more details that are coming up, which means that at any given point of time, the web map holds an immense amount of data. Like it's got data at varying perspectives, it's got data at varying levels of detail, and this is clearly a lot of data, right? Because as people who use web maps on a daily basis, we know that we constantly zoom in and zoom out. But in spite of it, web maps are incredibly fast. And why is that? The reason why this is so is because, one, you're always constraining the web map to a location that you're looking at. So, if you're looking at the map of Bangalore, there's no need for the browser to load the entire world. So you already reduce the amount of data that the browser has to load. And the second idea is that of tiles. A web map is basically a giant single quadrant Cartesian grid with slots for tiles. In computer speak, I think you can think of it as a matrix. So this is a map at zoom level 2 where you have 4 tiles on each row and you have 4 tiles on each column. And the origin of the map is in the top left, and every tile is uniquely identified. And how is this done? So the tile representation involves 3 different properties. These are Z, X, and Y, which stands for zoom, X, and Y coordinate. I mentioned earlier that it's a Cartesian grid. So you actually go from 0 to 3, and from 0 to 3 in the rows and the columns. And you also have the zoom property in every map that you're seeing. At zoom level 0, the map has just one tile, which contains the Z property 0, and the X and the Y are obviously 0. At zoom 1, the map has 4 tiles, so now the zoom remains constant at 1, but the X and the Y are varying between 0 and 1. At zoom level 2, you have the zoom property which stays constant at 2, but the X and the Y are shifting between 0 and 3. Basically, at zoom n, the map has 2 power 2n tiles, which is why at zoom 2, you have 2 power 2 tiles and 2 power 2 tiles. So that's 2 power 2 tiles on every row and 2 power 2 tiles on every column, so which makes it 2 power 2n. And the reason why the map is so fast, in spite of loading so many tiles, in spite of showing so much detail, is because of tiles. Tiles make it really fast, and secondly, tiles enable you to progressively load things. So for instance, if you're looking at, say, MG Road, and then you're moving on to Cubbon Park, there's no need for the browser to request the tiles for MG Road all over again. Like, it'll just request the tiles for Cubbon Park. Which brings me to my third idea of caching, that every tile that you request for is always cached. And fourthly, tiles are just very, very simple to imagine, even as an abstraction, because they're simply objects that are there in a Cartesian grid. But how does this style data really look to the computer? So when the computer is seeing the style data, it's seeing this data in two ways. One, as raster data, where it's loading the map as PNG images. Or secondly, it may be loading the tiles as vector data. This vector data is very similar to the data that we saw earlier in terms of the JSON structure, where you have the type and you also have a geometry. But in reality, this vector data is encoded as binary, which are called protofile buffers. So on the left-hand side, you have the JSON data, and on the right-hand side, you have an excerpt of this JSON data rendered in binary. This is the reason why web maps are so fast, because you're constantly just loading binary data. Vector tiles are the reason why they're so fast. Vector tiles can also be rendered client-side as opposed to raster tiles. So when you're actually requesting for a raster tile, the browser will send a request to the server. The server will retrieve the tile data, generate a picture from all that tile data and return this picture back to the browser. Whereas when you're using vector tiles, when the browser is requesting data, the data is given to the browser and all the rendering happens client-side. So I'm just going to wait for this slide to finish, because you can see that it happens really, really fast, and it happens very, very dynamically. And thirdly, vector tiles are very useful because they can be layered. So if you wanted to layer raster images, you would have to retrieve many, many tiles. But if you had to layer vector tiles, where, like one layer represents, say, all the trees in the world, you filtered the data to just extract the trees, that would be one layer. The second layer could have all the buildings. The third layer could maybe have oceans, and you could extract these layers separately, overlay them on the map, and this is completely possible with vector tiles. So essentially, parsing the world really, really fast, the first process is that you parse the world as vector tiles. Of course, this completely excludes things like image processing, which is not what my talk is about, but where what I'm actually talking about is that you're able to parse the world's data really, really, really fast because you're parsing binary data. And the second reason how you can make this parsing extremely fast is by using MapReduce. MapReduce is the process where you divide and process and aggregate data in a very parallel, distributed manner. But this is, again, a mouthful, right? So what do I really mean by this? Let's break down MapReduce, but in terms of vector tiles. What are the requirements for you to be able to use MapReduce on something? The first property is that the data should be able to be broken up into chunks, into very logical chunks that can then be pieced back, which is completely possible with vector tiles. Secondly, when you're operating on individual chunks and then aggregating the results of these individual operations, you're doing the same thing as operating on the large data set. So for instance, if you want to find out the number of buildings in the world, you would break down the world into tiles, you would find out the number of buildings in each tile, you would put these results together, and essentially you would be doing the same thing as finding out the number of buildings in the entire world. Thirdly, the chunks can be operated on in any order. So doing something like this is very similar to doing something like this or doing something like this. Before we move on to TileReduce, I want to show you a teaser of a video that we made when we tried to find out the road coverage on OpenStreetMap, and our benchmark was something that the CIA released, which is called the CIA's Factbook. This visualization is on a MacBook Pro, and it took about 20.5 minutes. Essentially, TileReduce is MapReduce, but on vector tiles. It was written by Morgan Herlocker, primarily by Morgan Herlocker, who works at Mapbox, and it's an open source library, so all of you are very welcome to use it. The reason why it's so incredibly fast and the reason why it's so incredibly simple is because it's 405 lines of JavaScript. I'm going to take an example of using TileReduce, And this involves filtering out all the roundabouts in the world as seen on OpenStreetMap. Here, our data chunks are vector tiles. The operation that we're going to be doing on each vector tile is finding out the roundabouts in each tile. And our reduce operation will be to aggregate all these filtered roundabouts. But what does this roundabout feature look like? I'm sure all of you have seen this when you've been driving or going on your scooter. These are these circles that you see anywhere. I'm sure there's so many of them in Bangalore. But as data, what this feature looks like is that it's a line string. It's important to note that it's not a polygon because it's not filled inside. It's a line string. And it contains coordinates, many coordinates, some of which I've skipped here. And most importantly, it contains a property called as junction, whose value is roundabout. Let us quickly look at some code and how tile reduce is really, really simple. All tile reduce scripts will have two parts. One is the main part, where you require tile reduce and make calls to it. And the second script is the map script. So this is a script that's running the map operation or the operation that you want to run on each vector tile. And this file will be called for every tile that's there in your tile set. So in our main script, we require tile reduce, which is an NPM module. We require any other NPM modules that we may require for our code. We then make a call to tile reduce. We specify the zoom at which our vector tile set is. We give the path to the map script. And then we have the sources array, which is an array of all the sources that you're operating on. In our case here, we're only working with a tile set from OSM QA tiles, and I'm going to give it the name OSM. Now, I'm going to move on to the map script, which is going to be called for every tile in this tile set. And what this map script does is that it has a tile layers variable, and this tile layers variable refers to our source. So you have this tile layers variable, and it's a feature collection. So you first assign this tile layers variable to this layer property, and this tile layers.osm.osm is your feature collection. And you iterate through all the features in that feature collection, and you see if every feature has a roundabout property. In the event that it has a roundabout property, if you're counting the roundabouts, you can just increment your count by 1. Or if you actually want to see the roundabout features, you will just write it to standard output. And also, every time this script finishes running, it has a callback that leads to the reduce function. And here, you're just incrementing the count for all the roundabouts in the world. And when every tile in this tile set has been processed, you can just write your output to standard output. And we were running this on an EC2 with all the data of the world, and it took about, just going to wait for it to finish, took about 15 minutes and 48 seconds, and we counted about 419, so that's 419,261 roundabouts. This is a visualization of the data, of the roundabouts data. This is all the roundabouts in Paris, and this is all the roundabouts in Dubai. One thing that I did not talk about when I spoke about the code earlier is that I've been saying that you can parse the world's data. You can also constrain tile reduce to work on areas that you're really interested in. So this is specified by something called a bounding box. And a bounding box, you can think of it as just a rectangle on the map. And this includes the minimum x, the minimum y, the max x, and the max y. So we do use tile reduce and Mapbox for more things than just making really cool maps. And I wanted to take you through some of the stuff that we've done with tile reduce. This project was where we tried to analyze building sizes in various countries, and building sizes and shapes in Monaco is what you're seeing on the screen right now. This is OSM Analytics, OpenStreetMap Analytics, which can be used to extract any sort of analytics about OpenStreetMap, like the density of buildings, the density of roads, where are all the roundabouts, all kinds of things. OSM lint is predominantly used to find errors in OpenStreetMap. OpenStreetMap is open for anybody to edit, and it's useful to run these scripts to just find out common mistakes that people are making and to maybe send them a friendly note and say, hey, maybe you should fix this. OSM tag stats was something that I wrote for someone who does not want to write code, who does not want to write JavaScript. It just involves like a simple command line command which extracts any feature from OpenStreetMap. You can use it to count features. You can use it to extract just the features. You can go check it out. Okay. This was what I spoke about earlier, which was comparing the CIA's factbook to OpenStreetMap. And this is how the coverage looked for India. So there's only 21% of roads that are in the world on OpenStreetMap, which is a call to all of you to go out there and map on OpenStreetMap. Something that I built in a really short period of time as an exercise was to study the gender of streets in many cities. As somebody who was quite interested in the idea of gender, this was a super fun project where I used TileReduce to extract the names of streets and then pass them to another library called NAMSOR to extract, like with some false positives, whether a street was named after a man or a woman. But the question is, why TileReduce really? Because there are so many other ways to process geospatial data, and why would you be interested in using TileReduce? I'm going to take an example where you try to count the number of buildings on OpenStreetMap. Traditionally, how you would do this is that you would download the entire OpenStreetMap planet file in XML format, which is a very, very big file. And then you would set up Postgres. You would import this data into Postgres using OSM to PSQL. You would figure out the table where the buildings are present, and then you would run something like this. But if you had to do this with TileReduce, you would essentially just download your vector tileset from this URL, OSM QA tiles, which contains vector tilesets for the world and for every country. And you would just npm install TileReduce. You could also repurpose several modules on npm which have been made using TileReduce, and then you would just write some code. And this code would look something like this. I'm not going to go very much into the details, but it looks very similar to the code earlier. You just have your main file, and you have your map file where you're looking for the building property. So what are the wins really? One is that TileReduce is incredibly fast. It is extremely fast. And it's also very, very accessible. For somebody who does not want to go through the entire process of setting up Postgres, you can write JavaScript, you can use it. Thirdly, you can also combine multiple sources of data very easily. Like this source variable that you see here is actually an array. So if you wanted to compare two vector tilesets, you could do that. You wouldn't have to set it up twice using Postgres. You can very easily constrain to specific areas in the world. You can make custom maps really, really easily. And you can also use it to just extract data and then machine learn with this data. But TileReduce does have a set of quirks. Some of these are that you have these properties or these features that are spread over many, many tiles. And when this is the case, every portion of this geometry is going to have a large, decimal value. Like they're going to be maybe 74.5, 6, 7, 8, 9, 10, something. And when that happens, to simplify, when you're breaking into tiles, some of these decimals may be cut off. And when that happens, you see these breaks at tile boundaries. And secondly, when you're generating tiles, it's a little difficult to accurately generate tiles for small areas, because when you do that at the boundaries, you're probably going to be including areas that you don't want. But this difference is pretty negligible when you're working with very, very large areas, which is predominantly the use case for using TileReduce. At this point, I'm going to stop, and I'm just going to say that I really hope I've given you a good teaser into using TileReduce, and I hope that you will use it to analyze any geospatial data that you may have, and I'm willing to answer any questions that you may have. Thank you.
The scripts that you just shown, so
very good question. So the difference between using OSM QA tiles and using Overpass is that OSM QA tiles are generated only once every day. So whereas Overpass is querying live data. So like if you can't use tile reduce to find out what happened this second. Yeah, for that unless you have a tile set of data that happened that second. Overpass is easier for that.
But there's a difference between the speed.
Yes, definitely, especially for very large areas. I'm not sure if you've used Overpass for very large areas, but invariably your browser will crash.
Yeah, it crashed.
Yeah.
Actually, I tried to find out the schools in India, so
Right.
it just almost crashed.
Right.
Will
So
that work with this or?
yes, it would be very easy with this. You would just need the tag value, the property and the value for schools, and then you could use tile reduce with that.
Okay, thank you.
Yeah, hello. My question is related to you are explaining about the JAD, which is related to the the zoom level, right? So my question is how we can associate zoom level with the satellite height or the altitude of the satellite if we are capturing the image. So suppose that if the user interested from the 20,000 kilometer above, 15,000 or the 1 kilometer above from the earth level.
I'm guessing that I'm not sure if I'm qualified to answer this question because I don't work a lot with satellite data. But I think satellites that are closer to the Earth are probably capturing images at higher resolution. So like with more detail. So the ones that are farther are probably lower zoom levels.
But my question very specific towards the what should be the altitude associating with the JAD. The zoom level.
I'm not sure of the answer.
Okay, next question is related to the zoom level. So you speaking about the number of tiles we are loading as per the zoom level to the power 2n, right?
Yeah.
My question, if my zoom level is not the natural number, it is the decimal, like the 2.5, how to handle that thing?
It's probably rounded off to the next biggest number,
No,
like when you're loading the tiles.
Actually, I tried with the Mapbox plugin, it is not working, it's throw me the error.
No, but we often use like zooms that are real numbers. So
that's what my question. If I have the zoom level 2.5, 3.5, 2.75, how to handle that? How many tiles will occur? Because I tried and it is not. It's giving me error actually.
okay, so the thing is, I think when you're working with, if you're doing this with tile reduce, like you need to have your tiles at the same zoom that you're interested in. So if you're using a map, like this process of real zoom levels is very easy. But if you want to specifically work with tiles at 2.75, there's this module called Tippecanoe that can be used to generate tiles at the zoom level that you're interested in, and then you can analyze it using that same zoom level.
Okay. Yep. Thanks.
Yeah.
Hi.
Okay, hi.
So can this tile reduce? I mean, you also talked about BBox, which kind of constrains this thing.
Yeah.
So does BBox accept a polygon as a constraint? So what I'm trying to do is just to address the same problem about at the end, where you have a polygon as a map and you want to kind of do a tile reduce.
Yeah.
So can I constrain a polygon?
So what you could do is there's something called tile cover, which you can use to generate tiles for a polygon. So once you have these tiles, then it's just a question of working with those tiles. So you would the first step would be to generate the tiles for the polygon. But you will still be working only with tiles, and this will not be a square, it'll just be many tiles.
So then what does BBox really do?
BBox, if you want to use just a rectangle. So in the event that you want to use a rectangle, you can use a BBox.
It's still a rectangle basically. That's what I'm
it
trying
is a rectangle, yeah.
It's not a polygon.
It will not accept a polygon value. Like BBox is very commonly used by people working with geospatial data. So I guess it's a useful, parameter to have for tile reduce to parse.
So what is OpenStreetMap's policy regarding mapping like sensitive buildings and government areas? Is there any policy we're not supposed to encroach or things like that?
So the idea is that all of the data is licensed under ODBL, but it's completely free for people to build even commercial products on. So there are areas of military that have been marked on the map. It's there on the map, but yeah. It just depends on what people want to mark, yeah.
Hi, just wanted to understand when things fall in the boundary, say for example a building, a tree or whatever it is, with so many number of tails, like how do you count it? Like do you count it as a 2 or 1? Like when
can you repeat it? Like do you mean
let
like
us say that you are counting some particular entity
Okay.
And now we are dividing into tiles.
Okay.
And a couple of these entities fall in boundaries. Say, for example, they come in both the tiles. Then.
Very good question. Really good question. I'm glad you asked. So the thing is, when a lot of this, when I spoke about, was associated with OpenStreetMap, and all of these features have unique IDs. So when you're counting, you're essentially counting those unique IDs. So, you know, in spite of having multiple features, these features will have the same ID, and you'll just be counting that number. So if you have your own vector tile set, it's best to have a way to uniquely identify each feature so that the count is accurate. Yeah.
All right, thank you everyone for staying. Special thanks for the audience who stayed back and did not show their backs to the speaker. We just really want to thank everyone for coming and being exceptionally nice audience. I also want to take this opportunity to thank the volunteers. All the people you saw here actually do other things in real life. We have students, we have people who run companies, we have programmers, so it's a whole host of people. If you feel like you want to buy them a cup of tea and chat with them, feel free to do that. I just want to thank Ujjwal, Adarsh. Some of us have come from quite far. Mukesh, Akshar, Kaushik, Harry, Anush, Santya, and Rahul. So thank you very much, guys, and good job. Thanks once again. See you next year at the Fifth Elephant.
Billy.
Hello.
Hello.
Ujjwal.